All right, so I guess we'll do the numbers. Minus 0.1 times 90 times 9.8 times cosine 60 times 30 meters. So work done by the friction force is 1300 joules. How much work is done by the rope on this sled in this distance? Okay. There's the rope. Okay, so what is the acceleration of this guy? 0. Okay, so there's the tension, there's the friction, and the component of the weight along the incline is mg sine theta. So tension plus the friction force minus mg sine theta is 0. So tension is mg sine theta minus friction force. And the work done by tension, again, tension and displacement are in the opposite direction. So work done by is minus tension times displacement minus mg sine theta minus the friction force times displacement. But we just calculated this in part 1. Okay, so that was 1300 joules. So we'll use that. So this is minus 90 times 9.8 times sine 60 times 30 plus 1300, oops. So you see the work done by the rope, the tension is about 15 times greater than the work done by the friction. Okay. So okay. What is the work done by the gravitational force on the sled? Okay. So again, there's the gravitational force, there's that component doesn't do any work, only this component does work. Mg sine theta and the displacement S. And you see the angle between this component and the displacement is 0 degrees. So the work done is cosine 0 is 1. So the work done is by gravity is mg sine theta times S. Okay. Okay, and that's positive work. And what is the total work done? So the total work done by gravity, work done by total, work done by tension, and work done by friction force. And what do we expect for this number? 0. Okay, so 22,915 minus 21,592 minus 1323. Okay, 0 joules, as expected. Okay. So again, this problem was, in this problem, all we did was calculated the work done by all these three forces. Yep.
Why would we expect it to be 0 again?
Here's the work energy theorem. So the applied force is negative of the spring force. Okay. So that's the applied force. Okay. And the work done by the applied force, dx, and you went from 0 to minus 10. 10 centimeters, so 0.1 meters. Okay. So the work done by the applied force is, the force is kx dx 0 to minus 0.1 meters. And this was 500 joules, okay. Oh, well, okay, let me write it like that. Okay. So this was 500 joules, okay, so K is 2 times the work done by the applied force, x final square. 2 into 500 joules. That's 1,000 divided by 0.01, so 100,000. Newton per meter. Okay, what does this number mean? Yeah, it tells you how stiff the spring is. It takes 100,000 Newton force to stretch the spring 1 meter. That's what that number means. Huh? Or compress it. Okay, stretch it or compress it. And 1,000 newtons, well, your weight is about 600 newtons. So 1.5 person. So 150 people would have to hang on to that spring to stretch it 1 meter. That's a strong spring. Your car has a 25,000 Newton per meter spring. Okay, so this is a strong spring. Okay, a bungee cord exerts a nonlinear elastic force. Okay, so the bungee cord is exerting a force. See, this would be a spring force, Kx, where K is the spring constant, and then there's a nonlinear term that's okay. And generally, when you do differential equations and all that, you'll do linear differential equations. This becomes a very hard problem to solve. Anyway, so as you stretch it more and more, the bungee cord pulls you harder and harder. Okay. And by the way, there's a typo, so that should be a negative as well. Okay. So here's a bungee cord. Yeah. And the bungee cord is applying a force in this direction, and if you're stretching it, you have to apply a force in the opposite direction. Okay. Okay, so a bungee cord exerts a nonlinear elastic force where x is the distance the cord is stretched. How much work must be done on the cord to stretch it 16.7 meters? Okay, so the work done by the applied force is equal to the applied force initial to final position. Okay, the applied force is negative of the bungee force, which is negative k1x plus k2x cubed. So as you're stretching the bungee is applying a force in this direction, and so you're applying a force in that direction. All right, so the work done minus K1 is minus 0.233x minus 204x cubed dx. And x initial is what? 0. Okay. So this is 0.233 by 2, 16.7 square plus 204 by 4, 16.7 to the power 4. That's the work done.
Sorry, I think you have your constants in the last one.
Hmm?
I think K1 and K2 got flipped.
Mm-hmm. So that's how much work is done in stretching the bungee 16.7 meters. And 16.7 meters is roughly the height of this building if you go outside. So when you jump off a bridge tied to a bungee, that's the amount of work that is being done in stretching the bungee. And who is doing the work there? Gravity. And that's why it's fun. You're not doing work. You're getting gravity to do the work. Okay. If you had to do work, then you wouldn't be paying money for that, All right, this says, how fast must a This says, how fast must a 3,000 kg elephant move to have the same kinetic energy as a 65 kg sprinter running at 10 meters per second? So this is a world-class sprinter. That's the speed at which world-class sprinters run. Okay, so mass of the elephant should equal the mass of the person. Okay. So V of the elephant is mass of the person, mass of the elephant. Okay. So mass of the person is 65 kgs. Mass of the elephant is 3,000. Okay, so the elephant to have the same kinetic energy as the person has to run at 15% the speed of the person. Okay, so 1.5 meters per second. So here's sort of this is a very rough argument. Okay. So the question is, why can't an elephant become too big?
Because you don't have to support the body weight. You have to supply enough energy.
And that's one of those things. And your metabolic rate depends on the volume per pound. If you're going to be a warm-blooded animal, you got to produce so much heat. So the amount of heat you're producing goes as your volume, which is 4 pi by 3 r cubed. So as your size increases, the amount of heat produced increases. And presumably you're getting rid of the heat by the surface area, which is only going as 4 pi r squared. Okay, so after a while, if you get too big, you're producing too much heat and you can't get rid of the heat. Okay. So for instance, let's say if you start running, you're producing more heat. Okay. And if you don't have a mechanism for getting rid of the heat, then you won't be able to run. So what is your mechanism for getting rid of the heat? Sweat. Okay, so once we developed enough sweat glands in on your body, you could run. When you could run, what happened? You could hunt. When you could hunt, eat high energy density foods. And then your supercomputer could grow. So if you were going to eat grass all the time, you wouldn't have that. All right, calculate the force needed to bring a 950 kg car to rest from a speed of 90 kilometers per hour in a distance of 120 meters. Okay, so let's convert that speed first to 90 kilometers per hour. Okay, the kilometer is 1,000 meters, so that's 1,000, and 1 hour is 3,600 seconds. So if you divide this number by 3.6, you get the speed in meters per second. Okay, so v square equal to v naught square plus 2ax minus x naught. So the acceleration you need is 0 minus 25 square divided by 2 times 120. The acceleration due to gravity is 10 meters per second square, so 25% the weight, the stopping force is 25% the weight. Okay? Well, let me do it that way. So this is equal to, okay, so the stopping force, calculate the force needed to bring the car. So the force you're needing is mass times acceleration. Okay, so the braking force is 27% the weight of the car. Okay, that's what that means. Did you guys understand that? Suppose instead, okay, suppose instead the car hits a concrete abutment at full speed and is brought to rest in 2 meters. Okay, so you see, if instead of 120 meters, now you bring to rest in 2 meters, that's in a distance 60 times smaller. The acceleration will be 60 times greater. That's bad for your health. Yep. So the acceleration would be 60 times greater. The stopping force will be 60 times greater. The stopping force is 16 times the weight of the car. No. And so if you get stopped over 2 meters as well, then the force on you will be 16 times your body weight. Okay. So what do safety devices do?
Extend your stopping distance.
What?
Extend your stopping distance.
Yeah, so the car gets stopped over there, so then you are there. You don't get stopped by the steering wheel, but by the airbag, and then crumple zones in the car, and so on. So you extend your stopping distance. All right, I guess we'll stop here because this is a long problem and I won't be able to finish this today.